We have been discussing noise and noise calculations. We said that just like we use frequency domain analysis for analyzing circuits with time varying inputs, we'll also use frequency domain analysis for noise. So for that, we had to describe noise in the frequency domain, and that is done through the power spectral density of noise. Okay. So after that, the circuit analysis itself is exactly same as with signals. Okay, because when you have noise, the noise will be represented as an additional small signal source. Okay, so all you need to know is incremental analysis, which is linear, right? And in fact, we will see it's exactly the same as how we analyze circuits for mismatch, except mismatch is, it is like mismatch. That is, mismatch is also represented by an additional source. These will be similar sources. Okay. Any questions on anything related to noise we have discussed so far? So we discussed how to calculate the output noise spectral density and output noise variance if you are given the input spectral densities. Now we will look at the noise spectral density of different components that we use. Okay. Any questions before we continue? So we saw that a resistor's noise, a noisy resistor of value R can be represented by a noiseless resistor of the same value plus a noise current source or a noiseless resistor in series with this is also noiseless resistor in series with a noise voltage source. The spectral density of IN is 4 kT by R and spectral density of Vn is 4 kT times R. These are what are known as white noise sources. The reason for the origin of this noise is thermal noise, that is random variation of random movement of electrons because it's at some temperature and because of the thermal energy there will be random movements. So a resistor has thermal noise and the commonly used model says that its spectral density is constant with frequency, and we'll use this, although we know this is strictly not true. This is good enough for our purposes. Okay. So the spectral density of noise current will be 4 kT by R, and again I remind you that this is the one-sided spectral density. Okay. So white noise basically means that noise at different instances are uncorrelated from each other. Okay, we'll see. We'll have other types of noise also, but this is fundamental, and this will be there anytime you have a resistor at this temperature. This T is the absolute temperature, so we will have this. Okay, and just to get a feel for the numbers, kT is 4 times 10 to the minus 21 joules. Okay, and this is of course at 300 kelvins approximately. Then for a 1 kilo ohm resistor, okay, SVN would be 16 times 10 to the minus 18 volt square per hertz. Now many times it's common to just specify the square root of this. Okay. The reason is to make calculations easier. Normally you don't calculate volt square, you calculate volts, right? You calculate the RMS value, not the mean squared value. This will become 4 times 10 to the minus 9 volts per square root hertz. These mean the same thing. You are just specifying the square root of that quantity, right? That's all. So this is square root of SVN or 4 nanovolt per square root hertz. Okay. The reason to do this is again for convenience in calculations. So if this noise goes through a bandwidth of 1 gigahertz, what is the output noise variance? If this noise is fed through an ideal filter of 1 gigahertz bandwidth, sorry, not 1 gigahertz, let's say 1 megahertz bandwidth. Okay, it's easier to calculate. What is the noise variance or noise sigma? You have to multiply it by the square root of the bandwidth. Okay, so you multiply the spectral density by the bandwidth and take the square root, or you multiply this by the square root of the bandwidth. If you have 1 megahertz bandwidth, you will get how much? 4 microvolts. Okay, so finally, when you have to calculate variances, the noise has to be band limited in some way. Otherwise, you just leave it at spectral density, right? This white noise is just a model. Integrating that from 0 to infinity makes no sense. You will always get infinity. But in real circuits, you will always have band limiting, as we'll see. Okay. Any questions about this? So this, with these sources, you can do any analysis that you want. And now we can go on to the other components. So you have a MOS transistor, and again, I'll use the simple model. You have some ID that is given by the MOS model, right? I'll still continue to use the three terminal model of the MOS transistor, but you get the idea. In reality, it turns out that the actual drain current will have another component. Okay, so just like with the resistor, if you are able to measure the instantaneous current, it will vary above and below the value that you calculate using this expression. Okay, so again, this can be expressed as a noiseless MOS transistor and a noise current source IN in parallel. Okay. Now it turns out in strong inversion, when the inversion layer is strongly inverted, when the inversion layer is formed strongly, you will have thermal noise here also. Actually, there isn't much difference between a MOS transistor and a resistor. Especially when VDS equal to 0, you can see it's the same. In a what you think of as a resistor, there will be free carriers always available. In a MOS transistor, you produce them by forming the inversion layer by applying some bias. That's all that is there. Otherwise, it's the same. The mechanism of current is what? In a resistor and in a MOS transistor. What is the current carrying mechanism? Drift, right? It is drift. So, in that case, you will have thermal noise. Okay. So, you have thermal noise in a MOS transistor, and in a strong inversion region, in saturation, that is when VDS is sufficiently high that the current doesn't depend on VDS anymore, right? That's what saturation means. The spectral density of this noise current is 1/3 kT gm. Some of these formulas may look weird initially, but they make sense. I'll explain how. Okay. Now you can see it's not all that different form wise from, for a resistor you would have 4 kT times G, that is 4 kT times the conductance. Here we have 1/3 kT times the transconductance. Okay. So this turns out it makes sense. I'll explain how. First of all, there is that extra factor of 2/3, right? And then instead of conductance, you get the transconductance. That's all. So this is fine. Okay. So we just use this model, and then we have this additional source. Once you represent it as some additional source, all you need to know is circuit analysis, and then you calculate the transfer functions from that source to everything else. Okay. Now, let me ask you this. Let's say I have a MOS transistor. This is the gate voltage, and I operate it with VDS equal to 0. That is, the drain and source terminals are shorted. Okay. What will the inversion layer look like inside a MOSFET like this, MOS transistor like this? How will it be? It will just be uniform. Okay. In fact, it looks exactly like a resistor, right? So what do you guess is this is of course not in saturation. This is in triode region. This is in deep triode region, right? So here also you can express the noise current as a current source in parallel. Can you guess the spectral density of this noise current? Given that we already said it is similar to a resistor, what is it? 4 kT times what? GM. What is the GM of the transistor when VDS is 0? Yeah, what is the GM of the transistor when VDS is 0? What is the expression for current in the triode region? Okay. So what is the expression for GM? What is the expression for GM? Mu CoX W by L VDS. You have to differentiate with respect to VGS. And what is the GM when VDS is 0? It is 0. Okay. So it's not 4 kT times GM. So what is it? 4 kT times the conductance, right? The conductance that appears between the drain and source. So in the triode region, this is true strictly when VDS equal to 0, this expression for the noise current is 4 kT times GDS. Okay. Now, what is the expression for GDS in the triode region? No. What is the expression for GDS in the triode region? Forget lambda. Let's say lambda is 0. How do you get the GDS from this expression? Differentiate with respect to VDS. Okay. So GDS in the triode region equals mu CoX W by L VGS minus VT. Okay. This is in fact not just triode. This is the expression when VDS equals 0. Okay. What is the expression for GM in the saturation region? Same. Okay. So GM in the saturation region is exactly the same as GDS in when VDS equals 0. Right? What is the, I mean, you have seen this expression, no? Mu CoX W by L times VGS minus VT. So that is the expression for GM in the saturation region. And it's also the expression for GDS when VDS equals 0. They are the same. This is assuming ideal square law, of course. So that way, although the symbol we use here, GDS and GM appear to be very different, the noise is almost the same, except for this factor of 8 by 3. I mean 2 by 3, additional factor of 2 by 3. Okay. GDS in the saturation region is very small. That is because of something else. In fact, the way we have written the model, the GDS in saturation region is 0, but it's not related to that. It's related to GDS in the triode region. Okay. Now this looks a little strange, but is there any other place where you have seen this factor of 2/3 come in? How many of you have taken solid state devices course? I only see half the people raising half the hand. I mean, so where else have you seen a factor of 2/3? Huh? Pinch off. But where? Why? Expression for what? Huh? Breakdown? No, I have never heard of breakdown. Don't tell me things I don't know. Huh? Parasitic capacitance. Capacitance. Which capacitance? In the what? I mean, capacitance is right, but have you seen the expression for capacitances of a MOS transistor? CGS is 2/3 WL Cox. So it's the same 2/3 that come in. Why is that 2/3 actually? Channel? Yeah. So it turns out there is a unified expression for noise that works in all regions. We won't use that because typically we are interested in finding noise in amplifiers, and in amplifiers you invariably bias this in the saturation region. Or you may be using MOS transistors as switches, and you have to find the noise due to the switch, and in that case you use the expression in the triode region. As a circuit designer, it makes sense to use two separate expressions, but it is good to know that it's not some ad hoc stuff. You have 2/3 here, no 2/3 there, and so on. Okay. So yes. Yeah. So first of all, see, we write these expressions saying that this is in the triode region, that's in the saturation region. It's not as though throughout the triode region this expression holds and suddenly it jumps to the other expression, right? It continuously changes. Okay. It does change continuously. So I'll just show you the total expression, but this can be used approximately anywhere in the triode region. Right. But of course, if you take VDS like very close to VGS minus VT, but just less, it is still technically the triode region. Then if you use the GDS from that operating point, it will not be correct. Right. Exactly. So this is close to VGS, deep in the triode region. This is correct, and well in the saturation region, that's correct. Okay. So it turns out that the unified model is, let me recall, it is 4kT times the mobility times the magnitude of the inversion layer charge, okay, divided by L square, okay. Now, what is the magnitude of the inversion layer charge when VDS equals 0? When VDS equals 0, the channel is uniform from drain to the source. So what do you think is the magnitude of QI there? Yeah, it is Cox is the per area capacitance. So it is Cox WL VGS minus VT. Okay. So this is when you have uniform channel between the drain and the source. And in the saturation region, what happens? The charge, obviously, the charge density is a lot higher here. And then in the saturation region, here it's pinched off. So eventually, the charge density goes to 0, right? Because at the drain end, the transistor is actually off. Okay, that gate drain potential is less than VT. So what is it? I mean, you can't guess by looking at it, but you have seen the calculation. What was the expression for QI? It is 2/3 Cox WL VGS minus VT. So now if you put these to here, L, the denominator L square becomes L, and you get mu Cox W by L times either VGS minus VT or 2/3 times VGS minus VT. Okay. So first of all, that will be either the GDS when VDS equal to 0 or GM in the saturation region. Okay. So there is this can be derived from the device physics also, but of course we won't use this. We will use either the saturation region expression or the triode region expression. Okay. Any questions here? Does it even have dimensions of conductance? I don't think so. Yeah, I guess so. It is. I mean, it, well, I can say that it represents GDS in the triode region, GM in the saturation. Okay. Yeah. So it's harder to write the formula. There will be some noise. Yeah. You're talking about moderate inversion region. I mean, it's not deep triode or it's saturation. Yeah, there will be some formula. You can use this. Okay. The expression for QI again will be something quite complicated. Right? No. I mean, see, the purpose of this, all these calculations is to take your design in a particular direction, not to get the answer to the third decimal place by hand. Okay, for that you have simulators. First of all, this square law model is so crude and so inaccurate that it's only used as guideline for your design. Okay, because I mean, this is, I mean, you must have heard the saying about measurement. You measure with a micrometer, you mark with a chalk, and you chop with an axe. Okay, that's not what you want to do, right? Okay, so you have to see where the errors come from. So for hand calculation, this kind of, even if you, let's say it is not VDS equal to 0, not deep saturation, but you use one of these formulas, you will get somewhere answer that is reasonable. Okay, after that you can go and calculate it. So there is no point calculating this very precisely when there are so many other sources of error. Okay. And actually, one of the things is in engineering, of course, you have to do accurate calculations. For that, you have computers and so on. But errors due to modeling can be much worse than errors due to calculation. If you assume like a flat earth and calculate many things very, very accurately to the 8 decimal place, many things will be completely wrong. Okay. So it's also important to model the physical phenomenon correctly. The accurate calculation, of course, I'm not saying it's easy, but you have to take, I mean, you have to use a computer for it and you can do that. Okay. So this is about thermal noise in a MOS transistor. This is also white. Okay, it means uncorrelated between different instants of time, and all the calculations, everything is exactly the same. Okay, and you can see mismatch also we modeled by an additional current source. So as usual, in fact, almost in every case, it turns out that you have two possible models. You have a noise current whose spectral density is 1/3 kTgm. I'll just use the saturation region expression. What is an alternative model that we can use? Voltage source at the gate. Okay. So what will be the spectral density of this? That divided by Gm square. So it becomes 1/3 kT by Gm. Okay. Typically we end up using this, but you can use that also. It's all based on convenience. Okay. We'll see. In fact, there is a utility to having something like this as well, right? So you can see, I mean, resistor, MOS transistor, the calculations will be very similar to that of mismatch. So which will also help you in the assignment, because last assignment, I think you calculated the effects of mismatch. In the next one, maybe you will do noise. And essentially, it's the same thing rehashed. Okay. Now, I'll quickly go to, like I said, lossless components like inductors and capacitors do not have noise, but we have diodes and bipolar transistors. And let's say they're operating with some current, some operating point current. Okay. And the diode, of course, is forward biased, and the bipolar transistors will assume that it's in the active region, which means it has a sufficient collector emitter voltage. Have you seen bipolar transistor models in the devices class? Or no? You have. Yeah, that's okay. But you've seen some model, right? You're aware of the small signal model of the bipolar transistor? What is it? It's the same thing as a MOS transistor, except you also have a resistor R5. That's all. Otherwise, it's the same. So now in these, what is the current carrying mechanism in a diode or a MOS, a diode or a bipolar junction transistor? It's diffusion. Okay. Essentially, you have charges like fired across the base from the emitter to the collector. Okay. So it's like having, I mean, we had this old device called a vacuum tube. In that, that's what it would literally happen. I mean, you have some heated plate, and then from that electrons would boil off and then go from one plate to the other. So what happens is these electrons are not these charges in BJTs or these electrons in vacuum tubes. They are not fired at some uniform rate. Okay, so there is some average rate, but the timing is random. Okay, and the timing is what is it follows what is known as Poisson distribution. We don't have to worry into the we don't have to get into the details of that. So because the timing is random, if you look at the instantaneous current, it will have noise as well. Compared to the average current, there will be some fluctuations above and below that. Okay, so it turns out, I mean, like with everything else, as far as circuit designers are concerned, all we need to know is there is an additional noise source, and you need to know where the additional noise source is, and you need to know the expression for the spectral density. Okay. So for the diode, it turns out to be 2Q times ID, where ID is the operating point current flowing through the diode. Okay. Q is the electron charge. Yes. Does it matter? So this is a zero mean random process, right? So that means it will have positive values and negative values and so on. So you don't have to worry about this. And also the noise from this component and that component are uncorrelated. Okay, so finally you will take spectral density, which is a positive quantity. That would be the same whether the current source is in this direction or the opposite direction, right? Spectral density of ion, what is the spectral density of minus ion? It will be the same, -1 square times the spectral density of ion, right? So it won't make any difference. So in the small signal model of the MOS transistor, we have the current source going from drain to source. That's why I put it that way. I mean, the drain current in the same direction, but it doesn't matter if you had put it the other. Only thing is, in a single calculation, you don't flip the polarity in the middle, because you could be doing calculations to two different things. The calculation from, the noise from different physical sources are uncorrelated, but you should preserve the polarity through the calculation, because depending on how you are calculating through whatever circuit analysis technique you use, in the middle of the calculation, if you flip the polarity, I mean, it won't work. Okay. That is, wherever ion appears, you use consistent polarity for it. You don't randomly flip signs, but you can use the source itself in any direction that you want. And then in a bipolar transistor, it is 2Q times IC, where this is the operating point, collector current. Okay. This is a different mechanism. It's called short noise. Okay. Short noise meaning basically you have electrons being shot from the emitter to the collector in an NPN transistor, and that while there is some average rate of shooting, the shooting itself is not uniform. So that's why you get this noise. That's why it's called short noise. Okay. Now these expressions look very different from the ones for the MOS transistor, right? Are they, or can you cast them in a similar form? So that there we had GM, here we have IC. So what is it? Can we recast this in terms of GM? So GM of a bipolar transistor is IC by the thermal voltage. Okay. So what do you get? You get 2Q times the thermal voltage times GM, or 2 times KT times GM. Okay. So expression again looks similar with some modification to the scaling factor. Okay. Is that fine? And the same goes for, this is for a bipolar junction transistor. and for a diode, this will be 2 kT times GD, where GD is the small signal conductance of the diode. Okay. So all of them follow a similar pattern. This just as thermal noise is fundamental to resistors and MOS transistors, the short noise is fundamental to bipolar transistors and diodes. Okay, because the very mechanism of current in a bipolar transistor is this firing of electrons from the emitter to the collector, and that rate is random, and that you will always get this. Okay, there are other types of noise which are little less fundamental, nonetheless important. We'll get to that, but this is very important. This again you can see is independent of frequency. So all these are like white noise. Of course, in reality, the short noise also is not independent of frequency, but again, for our purposes, we can consider that to be independent. Okay. Any questions? And of course, here also you can refer this to the base of the transistor if you wish to. Okay. That's a trivial manipulation, so I won't get into that. So all these components have noise, and now once you know the noise spectral density and circuit analysis, you can calculate the spectral density at any other place because of this component's noise. Okay. Now, it turns out there are, especially in MOS transistors, there is another important noise phenomenon that comes in. So we know that there are charges on, and the charges on the gate are balanced by the inversion layer charges and the depletion layer charges in the substrate. Okay. Now it turns out in any material processing, the interface between materials is actually very hard to keep clean. Okay. It turns out it's one of the most difficult things. That's why although the MOS transistor was conceptually invented before the bipolar transistor, it was practically realized only well after the bipolar transistor. Okay. Now what happens, it turns out, again, we'll only look at the results that are relevant for us. On this interface, this oxide semiconductor interface, there can be trapped charges. Okay. I'll just show that as some charge traps. Okay. So if you have those charge traps, now the charge balance should include those as well. Okay. I mean, earlier, if you didn't have any of that, it's just that the gate charge and the inversion layer charge plus the depletion charge should be equal to the gate charge. Now, you have these interface trap charges also. They will also come into the charge balance equation. Now, it turns out these traps also are not fixed. Okay. So, they can, they trap and detrap charges over time. Okay. And this is some random phenomenon as well. And it happens with a variety of time constants. Okay. So now you can see that even if you keep VGS fixed, every voltage fixed, because of this trapping and detrapping, what will happen? The amount of inversion charge will vary, and because of that, the amount of current will vary, right? Because what is current after all? It is related to the amount of inversion charge you have, right? So this is the phenomenon. We don't have to go into the details of it. So it turns out that this charge trapping and detrapping will also cause noise. Now this is not a fundamental noise process. In principle, this could be zero, but of course in practice it never is zero. But this you can see, I mean, if you have a very clean controlled foundry, it can be kept to a lower level than if you have a somewhat more sloppy foundry. Okay. So it's also related to how good the process control is. So in that sense, this is not a fundamental noise source, but it is always there, especially in a MOS transistor. Because in a MOS transistor in particular, that interface is very much part of the MOS transistor. Okay. So this leads to noise. And this is basically relevant only in the saturation region, because it's only if you have some other current that is flowing, that is the inversion layer charges are, let's say, moving, that is there is actually a current from drain to source, then the change in that number will also cause noise. If VDS is 0 in the triode region, there is no, this noise doesn't occur. So we'll just consider this only in the saturation region. Now, as usual, this can be represented, we'll start with this model. Okay. And to distinguish it from, let me just show it as IN. And this noise, the earlier one was called thermal noise, and this is called flicker noise. Okay. And it turns out that its spectral density is proportional to 1 by f, or inversely proportional to frequency. Okay. And this, there will be some constant. This is the operating point drain current, and you have L square, which is the length of the MOS transistor, right? L is the length of the MOS transistor. So it turns out to have this dependence. Okay. So if you plot SIN versus F, both on a log scale, what will this look like? This spectral density, it will be a straight line. What will be the slope? Really? What is the slope in decibels per decade? Is it minus 20 dB? This is power spectral density. It's minus 10 dB per decade. Okay. So when the transfer function is inversely proportional to frequency, the power will be inversely proportional to frequency squared. That is minus 20 dB per decade. This is minus 10 dB per decade. And on top of this, you will always have thermal noise, which is 1/3 kdgm. Okay. So by its very nature, you know that this flicker noise will be dominant at low frequencies, right? So depending on the bandwidth of the circuits you are working with, the effect of this flicker noise could be negligible also. So there are circuits for, let's say, very high speed links operating with tens of gigahertz or even higher. In that case, flicker noise may or may not be an issue. But if you come to, let's say, audio circuits or precision measurement circuits which operate at very low frequencies, then this flicker noise is a very big deal. Okay. And this frequency at which the flicker noise spectral density becomes equal to the thermal noise spectral density, this is called 1 by f. It's called f1 by f, or the flicker noise corner. So the flicker noise is also called 1 by f noise because of its spectral density. The reason is, I mean, you are familiar with flickering, right? It's some aperiodic, let's say you think of flickering of a light. It's some aperiodic turning on and off of that. And that also has a 1 by f type spectral density. So that's why it's called flicker noise. Okay. Infinite? Right. It will be, its value is infinity at DC. That's what you're asking. Yeah. So there are theoretical problems with this as well. This is a simplified model. So if you try to integrate this to infinity, I mean, the integral diverges. So, but there are many reasons why, anyway, that doesn't make sense. First of all, there are theoretical difficulties with this model. That is one thing. Actually, this integrating to infinity means that you're taking a measurement that lasts infinitely long. So that doesn't happen in practice either. So if you define everything precisely, that is, you are making a measurement from this time to that time, which is some finite time interval, and calculate the spectral densities properly, even that will go away. Okay. But for our purposes, it's okay. So there'll always be some lower frequency limit for integration in practice. Like for instance, if you're considering audio circuits, you don't care about noise below, let's say 20 hertz. Okay, so you will integrate from there to whatever the upper frequency you want. So in that case, you will get a finite integral. So we'll work with the simplified model, but yeah, it's true that there are theoretical difficulties with this 1/f type model. Okay. So the total, of course, both will be always present. The total noise will be the sum of these two. And at the flicker noise corner, the total noise spectral density will be 2x or 3 dB higher. Okay. 2 times in power is plus 3 dB, right? Okay. Now, this flicker noise is not exclusive to the MOS transistor. Actually, it will happen. It happens even in resistors. It turns out there are some similar phenomena which cause very slow modulation of the conductance. The conductance itself is not constant. There is some slow modulation. And similarly, even in bipolar transistors, it happens. But it's actually dominant in MOS transistors. In resistors, usually this flicker noise corner is very low. And in most regular circuits, it's not important. You can always find some circuit where it is important, but most regular circuits, we don't consider it. Same goes for bipolar transistors. The main reason is the following, because this the inversion layer of the MOS transistor is near the surface. Okay, and it's in the surface effects that cause this flicker noise. Whereas in a resistor, the conduction happens within the bulk, and there you don't have this type of problem as much. And similarly, in a bipolar transistor, things happen in the bulk within the, I mean, not at the surface. So this problem is a lot more severe with a MOS transistor than with a bipolar transistor. Okay. So we will use it whenever we have MOS transistors. We may have to calculate the effect of this flicker noise as well. Now, this flicker noise, the spectral density is not white, which obviously means that there is some correlation from one time incident to the next. It's a low pass type of noise, right? That is, the spectral density increases at low frequencies, which means that it's a sort of slow varying noise. Okay. Any questions? Now, we would also, just for flexibility of calculation, refer this to the gate. Okay. So what will be the spectral density of Vn? So Sin is some constant Id by L square 1 by F. So what will be Svn? What will it be? That divided by Gm square. Okay. So, and can you simplify this? What is the expression for Gm square? 2Id. I mean, let's not get Vgs minus Vt here. It is 2Id times mu Cox W by L. So if you substitute that, what will you get for Svn? What will you get? What do you get? What is that? Divided by Gm square. What did you do? K 1 by F by 2 mu Cox. Yeah. So the main point is that there is no bias dependence anymore, right? So this can be just termed as some other constant, K1 by F prime or something of that sort. So it is just inversely proportional to the area of the MOS transistor. Okay, and 1 by F. Okay. So in a way, you can see this is this formula, this inverse proportional to W by L is reminiscent of something. What is it? What was it? Variance of what? Yeah, every variance was inversely proportional to WL, but this one in particular is similar to which one? Which mismatch is this related to, you think? Threshold voltage, yeah. So you can see basically you have this capacitor here, and then you have some fixed charges like fooling around. So that will essentially this change in the charge divided by this capacitance will be like a change in the threshold voltage, right? Because it's like having additional voltage on the capacitor. Okay. So this looks very much like this is when referred to the gate, it looks like the expression for I mean it has the same dependence as the expression for the threshold voltage variance, right? So the larger the MOS transistor, the lesser the flicker noise. Okay. So now this again, like with mismatch, it gives you some trade-off between precision and area and so on. Of course, you have a larger MOS transistor, you'll have lesser flicker noise, but you'll have more area and also larger capacitances, which you'll have to drive and so on. Okay. Any questions here? So sometimes it's convenient to have this model, that is SVN, which is independent of bias. Okay. Otherwise, you'll have to, as ID varies, you have to keep track of that. Whereas when referred to the gate, the flicker noise model is independent of the operating point. Okay. Any questions about any of these? So as far as we are concerned, we only need to know the models. For every component, you can either refer it as some current or some voltage. Okay. This is true of mismatch. This is true of noise. And you need to know what the spectral density is of each of these noise sources. And then you have to be able to calculate the transfer function from this noise source to the output quantity, whatever that is. Okay. So we can go through an example calculation. Let's take a very simple circuit which also illustrates some other points. What circuit is this from VI to VO? Low pass filter. Okay. What is the transfer function? 1 by SCR. You are mumbling the like most crucial part of the answer. Okay. So now where is the noise in this circuit? Resistor. Okay. Would it be convenient to use a voltage source as a current or a current source as the model here? Voltage source. Why? Because we already calculated half the answer, right? So if I have Vn here, so what will be V naught by Vn? Obviously the same. Okay. So now what will be the spectral density of the output noise voltage? So at VO there will be noise because of resistance, right? What will be the spectral density of that noise? Yeah, what is the spectral density of Vn? Huh? 4 kTr times mod of 1 plus and what should I substitute S with here? It is J 2 pi F. Okay. The spectral density is invariably calculated as a function of the cyclic frequency F. Of course, you will see examples of omega also, but in our case, we always do it with the cyclic frequency F. So this becomes 4 kTr by 1 plus 4 pi square F square C square R square. Okay. So the spectral density, as you can see, goes down with frequency. Okay. What will be the output noise mean square value or RMS? How will you calculate it? You have to calculate the variance of this noise, which means you have to calculate the, you have to integrate the spectral density from 0 to infinity. So please do that, and we'll continue the discussion in tomorrow's class. It's a very easy integral. Okay. Any questions? Okay.